be moderating this panel. So this panel is about future directions in applied mathematics for, I guess perhaps the next 50 years, or who knows. Let me, a couple of logistics remarks. This panel is being videotaped, camera right there. We're not actually using a microphone up front. The camera can capture us very well. So that also means that the camera can capture you. So obviously we would encourage questions and discussions with the audience members. But I guess the advice is that if you don't want what you're saying to be captured on camera, then you might want to do it very quietly. Okay, so that's the logistics. We're going to start with, so I will introduce very briefly just the panelists, and then they'll introduce themselves and go over their expertise and their experience and so on. And after we've done that, then they'll have an opening statement, and after that we'll go to broader discussions. Peter Schmid, you're a soils planner this morning. He's currently a professor of mathematics at Imperial College. Next to him, Chris Jones, a professor of mathematics and applied mathematics at University of North Carolina, Chapel Hill. Next up is Tung, professor of applied mathematics at the University of Washington. Next to him, Greenbaum, professor of applied mathematics, also at the University of Washington. Next, Kutz, also professor of applied mathematics at the University of Washington. And last is Chris Bretherton, also professor of applied mathematics and professor of atmospheric science at the University of Washington. I should also add that I've been asked a couple of times, why aren't there any young people on the panel if you're going to talk about the future of applied mathematics? I think young in that question was relative to whoever was asking the question. So younger meant like, how come everybody on the panel is older than me? Is basically what the person who was asking the question was asking me. In any case, we have a lot of expertise up front. We have a lot of expertise in the room, and a lot of hopes and aspirations and who knows what in the room. So hopefully we'll get to all that with the questions and the discussions. So Peter, go and introduce yourself, and then after that we'll go to opening statements.
Okay. All right. So my name is Peter Schmid. I used to be in this department for 12 years, from 1993 to 2005, then moved to France for 9 years. Worked at the CNRS, which is the National French Research Association. And then 6 years ago, I moved to Imperial College where I'm in the math.
I'm Chris Jones. I'm at the University of North Carolina at Chapel Hill, where I've been for 15, 16 years. Before that, I was at Brown in applied mathematics. So then I was a professor of applied mathematics. And I work in applied dynamical systems. I've been interested in the ocean for about 25 years, working with oceanographers, and then climate and related things more recently.
I'm KK Tung. I've been in this department for 30 years. This is my 30th year anniversary. My training were in fluid mechanics, but I've always been in the applied math department, and I've been in soil sciences. And as I talk today, I mentioned that I'm recently doing oceanography.
My name is Anne Greenbaum. My area is numerical analysis, especially numerical linear algebra. I've been at the University of Washington for about 25 years, but a lot of that time was spent in the math department, and then I moved over to applied math somewhere around 10 years ago.
I'm Kutz, applied math department. I've been here, I guess, about 20 years or so. Came here for my postdoc at Princeton, where I worked with Phil Holmes. Most of what I used to do was applied dynamical systems, not only waves with application in optics, and I've moved more towards now data science, machine learning, and integrated dynamical systems, and broadening out to some new areas like neuroscience, among other things. So.
I'm Chris Bretherton. I came to the University of Washington in 1985. You do the math. I started out in the Department of Applied Math here after doing my graduate work at MIT in mathematics there, but with an advisor from atmospheric science. And after a few years, I took a joint appointment in atmospheric science. So my interests are in atmospheric science and climate, and in particular numerical simulation of clouds and turbulence in the atmosphere, in actually doing field work. I go out in the field and fly in research aircraft sometimes. And most recently, I've actually also started becoming interested in machine learning and had a couple of people working with me on that. And in fact, on Monday, started a job at Vulcan, which is in the International District, as their senior climate director in charge of a program on machine learning for climate modeling.
Okay, thank you. Peter, do you want to start with opening statements and then?
Sure. Okay. So it's the future about mathematics. So I guess you all applied mathematics. So I guess you all expect some kind of a prediction or something like that. So but I think there is a Mark Twain quote that says it's very hard to predict anything, especially the future. So in preparing for this, I thought I would look back a little bit and see what actually surprised me during my years in applied mathematics. Some kind of order 1 changes that came out of left field. And they didn't just change the way we do things more accurately or faster, but they changed things we do differently. So I came up with 4 somehow techniques that somehow impacted me, or at least piqued my interest. And that was uncertainty quantification, randomized algorithms, compressed sensing, and recently machine learning and deep learning. So these were 4 things that all went through the usual stages when something new comes on, some order 1 changes, the surprise, the euphoria, the bandwagon, the frenzy, and then the low-hanging fruits wash out, and then settles into a more balanced, settled state. And I think we're going through something like this with the last one in machine learning at the moment. They all did a little bit what we always call a paradigm shift. It's an overused word, but for example, not everything that we compute is needed. Not everything we compute is as accurately as we need it. Essential information is incredibly and surprisingly sparse, and things like that. So I think I just leave it like this. And,
Okay, so let's see, 50 years, that's what you guys said?
Whatever time I'm in.
50 years. So 50 years, I don't think you can predict really in any way the way that math or science is going to go. But I think you can make some sociological suggestions about how the sociological development of applied mathematics will occur, so what's important to it. And I would think that we in applied mathematics are sort of used to taking a second row seat to pure mathematics somewhat. I think and we've sort of done that rather happily. Applied math departments are much smaller than math departments, even where they exist. Applied math programs are fairly small units within math departments very often. And I think that's going to change, that's going to have to change, and we're going to be called upon to take a much greater leadership role in mathematics generally, because the case is going to have to continually be made and made stronger and stronger that mathematics is relevant to the world. And as I can see it, pure mathematics community is shying away from that, although they do have some great examples. The other thing I think one can say sociologically is that we're going to have to figure out how to empower all communities in this country to be a part of applied math and generally STEM enterprise, and that is we're going to have to figure out how to get Hispanic and African American communities really a major part of what we do, rather than just paying sort of lip service to diversity and so on. We're really going to have to change that. So, on the math and science, I would say on a time scale of 10 years, one can say that data is going to be very important. That's sort of clear. We've heard that a lot today about machine learning becoming sort of important and prominent in the area, and as Peter says, came out of left field a little bit. But I think we in applied mathematics are going to have to figure out what role data is going to play and how to balance that with modeling. So I think we're in danger of data science kind of swamping modeling. It reminds me a little bit of when I first got into talking with oceanographers in the late 80s and early 90s. There were a large group of people who sort of believed that applied mathematicians were kind of a temporary evil, that they would tide us over until our computer programs were highly resolved enough that they could answer everything. I mean, and there were people who really believed this, that we were moving towards being able to basically replicate everything by having very high resolution computer programs. And that applied mathematicians would be needed in the meantime to cross the scales. Of course, the fallacy in that argument is that there's always a finer scale, for one thing, and it just is not true that the computers can answer everything, and you have to have a good base of physical understanding. And something I'm sort of worried about in the current atmosphere is that the same kind of feeling about data. That data is going to basically be able to answer everything for us. And I think that's also a mistake, that we have to remember that if we're going to predict anything, that has to be done on the basis of physical laws and physical understanding, which are channeled through mathematical modeling. And that has to take a seat alongside dealing with data.
I wasn't supposed to be on this panel. Professor Hong Chen was supposed to be in his place, and before he left, he told me what he wanted to say. So some of the things that I would say probably reflect his opinion. But let me first say something from my own opinion, which is not really opinion, but just a retelling of the history of applied mathematics. The oldest applied math department is started in the 1940s at Brown. And the problem at the time, which Professor C.C. Lin was working on as a applied mathematician, was an asymptotic problem. This problem arises on the instabilities in shear flows in the boundary layers. And normally one would think that if you add viscosity, it dams all the instability. However, this instability actually arises because of the viscosity. So the add damping actually creates the instability, and that instability was thought to be what causes turbulence. So it was a problem that Heisenberg in physics couldn't solve, and C.C. Lin then have some very intricate asymptotic analysis and find out why the viscosity destabilizes the flow and plot out this boundary where instability arises. Now, as we go forward, as Chris said, this probably was temporary until computer with finer and finer resolution will be able to do it. But there's always a high enough Reynolds number, small enough viscosity where this phenomenon is confined to increasingly thinner and thinner boundary layers. And asymptotics is great for these singular problems, while numerical analysis will be good for ones where you can resolve the boundary layer. And so I would say that some of these mathematical techniques will still be useful in these cases. So what should the direction for us for 50 years? Well, the question that was asked for the next 50 years in our 50-year anniversary, I think has a component that says, what should the applied math be in this department for the next 50 years? The other component is what the applied math field should be in the next 50 years in general, not related to this department. I think we can address both issues. But with respect to this department, if you want to say what is the applied math department should be in the next 50 years, then you have to consider what's around us. We have statistics department that do a lot of empirical modeling. There is a computer science department that does a lot of artificial intelligence and deep learning, etc. So where should we fit? Where should our role be? I think we should be very cognizant of this, the role we are in here, where we fit, where we should make the most contribution in this environment, in this university, taking into account what's around us.
One thing that I think is going to play a more important role in applied math and numerical analysis is randomization stochastics. In our department, we've started a sequence in stochastics, which we didn't have before. And I think that's a very good thing. I think people will need to know analysis, numerical analysis, and also stochastics, probability, statistical analysis in order to do a good job on the applied problems that we are looking at. One particular thing that I have predicted something about and been totally wrong about, at least so far, is computer arithmetic. We are used to working with 16 decimal digits, essentially. That's the machine precision. And as long as our problems were on the order of 1 million or so, that was fine. We had error estimates saying that round off would grow like maybe n squared times the machine precision. And as long as n squared is 10 to the 12, machine precision is 10 to the minus 16, everything looks great. You get your 4 digits, you're happy with it. Now n squared may be 10 to the 16, and I keep waiting for people to ask for more precision, but I haven't heard it yet. In fact, it's going the opposite way. People are using half precision now, and I think this computer arithmetic, we sort of went through a phase where every computer did arithmetic differently, and that was a very confusing phase. And then we got IEEE arithmetic, and all computers did arithmetic the same way, and that was a nice stable phase. I think we're going to go through another unstable phase as far as computer arithmetic. So those are the couple of things that I've thought about. And I should also mention that I'll put in a plug for the session tomorrow afternoon on the numerical analysis curriculum and how that should be changed or, perhaps modified in the future.
All right, well, I do a lot of data science now, and I think this is, of course, an emerging field. There's a lot of talk about it. I think maybe it's overblown in some cases, but I think the use of machine learning AI type of architectures for applied math, I think, would be very powerful for us. First of all, because of, I think, the computing abilities of applied math people in general is consistent with what the kind of skills you need for these kind of architectures, but also our connection to the engineering sciences. A lot of us in the department work in application areas where I think there's a lot of misuse of machine learning there, because it's so easy to use products like PyTorch, TensorFlow to just throw all your data in a deep neural net. I got something, and not really understand what that is. And I think what applied math has a role to play there in this emerging data science areas to bring back some sanity. It is another tool, just like computing is for us as a community to use, just like we have in computing PDEs and solutions to complex systems. In fact, I would say that for us, I think one of the challenges we have as a community is how do we imbue our students with all of this knowledge, because now we're adding a whole new dimension to the training that needs to be there when people are already loaded up with all the things they need to know, and now you've added a whole nother thing of data science as well that needs to be there for them to, I think, be effective in the next 10, 20 years. If someone does, you should be able to, in other words, solve a heat equation by discretization and running a simulation. You should be able to also just as easily be able to train a neural net to do some data analysis or to do some other kind of machine learning on that. You have to be proficient in both, I think. What I'm hoping to gain out of this and with these new tools is something that I think many of us, like I think Eric back here and myself would like to do, which is, when you come into problems like neuroscience, what we really need to start thinking about is how do we handle multi-scale networked dynamical systems. These are really difficult problems that I think we need new mathematical tools. It's the same also with Chris doing atmospheric science. We have large multi-scale systems. We're really good at uniscale physics. We give you one model, go solve it, say something about it. But what happens if you have different models at different scales, all interacting? And I think we're getting to a point where we have a whole new set of tools to maybe try to go after that. These are really hard problems. I don't know how much progress we'll make, but we certainly maybe have the tools to start making some progress along that direction. Or at least that's what I'm hoping.
Okay, well, going last, I will have very little to say, I guess. But I did want to reflect on a couple of different points. One of them is, of course, our future is our past, and applied math in the future will have, in some philosophical way, a huge connection to applied math over the last 50 years. And in particular, from my own point of view, maybe as a more applied person, I regard applied math, among other things, as involving the construction, solution, analysis, and simplification of models of interesting systems. And what those interesting systems are has varied a lot over time. I think when I came in, there were a lot of fluid systems, solid mechanics. We moved to math biology. Now we're interested in stochastic systems, mathematical finance, very complicated neurosystems, ones where the model is brought to us by data and machine learning as opposed to by any kind of fundamental equations. But the fact is we're still doing, I think, in many ways the same thing. And in particular, the point about that is that what distinguishes applied math from other fields is that we expect people trained in applied math to be at least conversant with all of those things. You can make models, you can solve models, you can analyze models, you know how to make toy models that simplify the ones you have, and understanding all of those tools together allows you to be take a much more powerful approach to solving real problems. So another thing that I think gets to an issue that Nathan was talking about, which is how in the heck do we learn all this stuff, is that we're standing on the shoulders of giants here. And in particular, I think in my own career about what's really different from when I was a graduate student to now. I can think about different new mathematical methods, but I think the most transformative thing has been the internet and the web. And the internet and the World Wide Web basically gave us a framework to collaborate with each other a lot more efficiently. They gave us a way to get giant data sets to our own desktop so that we can work on them without having to drag a tape drive, drive a tape drive from Philadelphia to get it here, or to put punch cards in the machine. And so they've been transformative in terms of our ability to actually work across all of these fields at once. Okay, a couple of other thoughts. I think, again, what distinguishes applied mathematicians is that models we have right now, modeling systems, are getting increasingly complicated. This morning I talked about climate models, but we have models, self-driving cars. They're just like amazingly complicated. They're made of a lot of sub-models. And most people in applications fields treat those models as black boxes. So, as applied mathematicians would taught not to treat the model as a black box, but to poke at it, break it down, to think hierarchically. And so we make a great part of an interdisciplinary team, I think. We're much more skeptical about models. We ask how they're constructed, we try to make them better. And I think that that's something that applied mathematicians will have to continue to work on in the next 50 years. So I mean, I see in the next 50 years, we're changing our tool set all the time. Now we have to be good at statistics, linear algebra, optimization, machine learning, stochastics, but the philosophy is still the same, and really the mindset is still the same.
Before we start a wider discussion, KK, you said you were partially here to represent Hong Chen. Did you get to his quiz?
Not yet.
You want to do it now?
Okay. I went to a thesis defense by Hong Chan's student. Tung was his last name. His first name was, I think he got one award.
Hong Chen, just general.
Yeah. No. It's general exam? Defense. I think it's defense.
Oh, okay.
Yeah. Now, there's something struck me when I was sitting in the audience. He says that if you look at individual cells, then you can treat them perhaps as random entities, and so you do some random random dynamics. And on the other hand, if you treat the whole organisms consists of many of these cells at a macroscopic level, then it's governed by Newtonian mechanics and some constituent equations. This is right in the middle, at the mesoscales, where you have a collection of cells, a population of them, or many cancer cells, etc. That's where the mathematical description becomes one about probability density function. And there is a well-accepted, and I don't think anybody would argue with the equation for Boltzmann's equation, which describes probability density functions. And it could be derived very easily under some very general conservation laws, and from which you could derive many other things in different limits. But in this region, where you call the mesoscales, is where we could do deductive mathematics. That is, applied mathematicians have always been good to use Newtonian's mechanics as theory, and then you deduce things from it. Here we are in the mesoscales. It's no longer Newtonian's mechanics is no longer valid. So what are the different regimes? What are the equations with respect to biology, to living cells, to a collection of living cells, to the non-equilibrium dynamics of non-equilibrium thermodynamics of living cells? These are the issues that the physicists probably should be doing, but they are not doing it because this is biology, it's not physics. And this is where we could come in. And Hong Chen sort of want to push, in addition to a completely empirical approach where statisticians are probably used to, that there is a deductive component to the future of applied mathematics, where applied mathematicians are well suited to make contributions to, and where physicists are not yet in that field. And so he made some, I think Hong Chan made a lot of developments on the thermodynamics of living cells, where in the Boltzmann's entropy equation, the entropy just keep increasing. But when you have a collection of cells, there is a biological activity, so there's a production, and there is then dissipation, and then you have a force acting on it, and so the non-equilibrium thermodynamics of living cells and collection of living cells are very different. And so these are unexplored territory, and with the kind of stochastic differential equations, the expertise we have, and the Boltzmann's equation is a stochastic PDE integral equation. He thinks that applied mathematicians could make contributions in that direction, and it's a very broad field, difficult field. It probably would take us 10, 20 years.
Thank you. So, are there any audience questions for any of the statements that have been made in these opening remarks?
I just wanted to ask, I don't know if there's an answer, but what do you think determines like the current tools? You were talking a lot about how the tools are changing, but our philosophy is still the same. So I was just curious, like, because machine learning has been around for some time, but it seems like now everyone's doing machine learning and it's really taking off. So I guess my question is two parts. What do you see coming next? And is there any way to predict what's coming?
Chris, I think this was correct.
Oh, well, I'm with Mark Twain on that. I'm not predicting the future. I mean, I think what makes tools really develop and flourish is that they're easy to use. And that's really what has distinguished machine learning in the last couple of years. We have a tool that has become easy to use because a group of people has basically built a software framework that makes it easy to use, and we now have a hardware framework which supports that software framework that makes it very efficient. And when I think back on things like MATLAB, for instance, okay, numerical linear algebra was definitely a thing in 1980 when I graduated from Caltech, but my entire numerical linear algebra class was not taught with a single computer, and now I'm intrigued about doing that. It's just why we need to bother, because that's why we do numerical linear algebra, is to use tools like MATLAB and Python that allow us to solve important problems with it. So it's the availability not just of theory, but also tools that make that theory accessible to students. Is really important. And I think the same thing applies to things like optimization. And so as tools develop, we just have to adapt to use them. And I think it really is a process of adaptation. Things do come in from left field, and we should pick up the tools as they arrive. I don't know what they're going to be.
Can I take a shot at that too? So I agree that I don't think we can say what the next tools are going to be, but maybe we can have an idea of where they're going to come from. So machine learning is, as Chris just said, sort of a tool that's been well developed and now easy to use, but we don't really understand why it works, do we? I mean, it is kind of a black box. It is sort of a mystery, and there is this idea that it's through neural nets. It's somehow mimicking things that our mind does, but we don't really know why it works, and we also don't know perhaps yet when it won't work and what its limitations are. And it seems to me the study of that, which is exactly what we do as mathematicians, applied mathematicians, of why something works and where it will not work, what will break it down, is where we will see the next tools emerging from.
So I want to ask you if you think that in the next 50 years, education in applied math is going to become more intensive or maybe longer in the sense that new models arise as a combination of old models and new fields arise as a combination of other fields.
I think it's going to be hard to walk away from the time frame we have set for a PhD for ourselves and also to incentivize students to come in. I think that we're going to probably, when you decide to work with one of us or whoever your advisor happens to be, you probably tailor some of your skill set around that person. And obviously you're going to be shortchanged whoever you work with. But that's always been true, right? No matter how this goes down, if you did a PhD, you had massive holes in your educational background that you needed to fill in as you went. I think that's an interesting thing now is there's so much educational tools available online that this generation is much more broadly aware, I think, of the stuff that's going around in the community, because you can go say, hey, I wonder what this person works on. Undoubtedly, there's a YouTube lecture that they give with a high-level pitch about their stuff, and you're hearing from potentially the best person in the world. So you even have some of the key vocabulary terms. You may not be interested in it, you may not delve down into it, but you at least understand kind of ballpark what they're doing. And I almost feel this to be like almost knowledge on demand. You're going to work in an area, and when you realize I need some of these tools, you're going to be able to very quickly go and get those resources. You know, it wasn't that long ago, right? When I was in grad school, well, maybe it was. But you know, if you wanted to get a paper, you walked over to the library and you copied it off for 5 cents a page. So you really were making a commitment. Do I really want this paper? It's going to cost me time and money. Go get it, and then you save that piece of paper. Whereas now, you just Google, so you pull papers in and out, read the abstracts. It's very easy to sort of pull this information flow for you. So your ability to access broad knowledge, and I think that's actually a strength of this younger community, is that they already grew up with this of figuring out how to go get stuff. And I think what will happen for us is you're going to be able to follow these streams and bring it into the research as you need it. Because there's no way we can teach you all of this in your program. And we're not going to make you 20-year PhDs.
I may just add to that. And the skill set also changes because everything is so easily accessible. And now it's not, the effort doesn't go into getting something that you know you need. It's finding out what you actually need. So the information is just overwhelming. And knowing exactly the method or the paper or the algorithm or the program that helps you further along in on your problem, that's the skill that is now necessary more than it was before.
Do you see the interplay between academic institutions and industry changing over the next 50 years? Like, I think there's more papers coming out of industry now, perhaps, than compared to the past. I'm curious if you may have noticed something on that regard.
It's probably driven by the machine learning industry. We see Google publishing, right? We see Facebook. We see these kind of companies that are involved in developing neural nets and playing with it, going to conferences and actually publishing things that are just as academic as something that comes out of the university. So in that area it will change. In others it probably will not change as radically as these ones.
So I guess I'd like to add. So I would think that goes in cycles, right? So Facebook and Microsoft and so on, so they have research groups now.
Yeah.
But Chevron and IBM and a lot of those companies used to have research groups that are, I mean, even Boeing has had a very academically active research group, but people are doing research right now. If they choose to publish, they're doing it on their own dime, as opposed to being, right? So I think that there are cycles where those things change from some companies and it goes into different directions.
Absolutely.
But I mean, I do think that existed before as well.
Yeah. when I was a graduate student, for example, they had a very active research group at IBM Jefferson Heights that was just like an academic department that developed numerical analysis techniques and so on. And then they totally shut down. And now we see places like Google. They have a Google campus. They almost want to be like a university. So it does come in cycles.
One thing that surprises me is how slow we are to adjust to our curricula to the needs of industry. I mean, so I was at a meeting a couple of years ago with the people from Facebook there saying, you know, you have to start teaching linear algebra earlier. There is absolutely no reason why linear algebra should wait for you to go through the entire calculus sequence before you can take linear algebra. And linear algebra is the foundation of all this stuff that we're talking about. And why are we not now teaching it much earlier? Why are we not teaching it as a, an applied subject that can be useful in this way? And we're missing out on a lot of this data science stuff because we're stuck. And we are so resistant to changing curriculum. And it seems to me that's something that's going to have to change.
I couldn't agree more. Yeah, 3 years or 3 semesters of calculus before you see your first matrix.
Which has nothing to do with calculus.
No.
I wanted to repeat 2 themes that I've heard the panelists say and then ask a question about them. The first that everybody seemed to articulate was the embracing nature of applied mathematics, the fact that it does not construct borders between disciplines. C.C. Lynn didn't reject the problem of instability because it was coming from a physicist. Atmospheric scientists don't reject, or applied mathematicians don't reject atmospheric science questions because they're understudied in A and OS departments. And applied mathematicians don't reject the study of discrete mathematical phenomena in algebraic systems because they are coming from computer science engineering systems. So the idea that we embrace topics coming from different departments, but also that we embrace methodologies coming from all sorts of different fields that are inherently mathematical, both statistics, top-down and bottom-up approaches. That's something that I heard, and that is something that also seems to be amazingly rare and almost magical about applied mathematics, as those of us who might have considered teaching the type of approaches that we blend together in departments with other names that have discovered. The other piece is the remark that we're so driven to discover the essence in a skeptical way of why it is that systems work. I love Chris's remark about the sort of quest to understand ML systems, machine learning systems, not as black boxes, but as mathematical operations. And that's also rare and magical, I think, within applied mathematics. If you go to a machine learning conference, you might find that 1% of the papers have that cracking the black box attitude. But if you look at the 3 people in our department working full-time or part-time on neuroscience, Ellie, Nathan, and myself, you'd find that half or more of our work is exactly driven towards cracking that black box versus building new ones. So the question is, how do we take these 2 pieces, one of which is an embracing one, and one of which, as Chris articulated it, is a philosophical one, and use this to define a cohesive mission for our department. It doesn't look like we're some amoeba that spreads across and embraces all fields and all disciplines, but rather notes that we're sort of a special beacon or lighthouse or something that actually takes from all fields and all disciplines and drives without exclusion, without partitioning, drives towards really identifying the sort of essence of why the world works towards it does, the way it does.
So, just comment. So, one thing we don't do much in our curriculum, though we certainly could do more, is sort of more of a case study type approach, which is, Fred 1 used to teach a course on mathematical modeling, which tried to have this flavor, but, pose a problem which requires a blend of techniques to solve, and have courses whose primary focus is to sort of the synthetic role of bringing techniques from different parts of applied math, or just generally different ways of thinking together. And as I said, other fields like law, for instance, you can use this very effectively. I don't think we do this very much in our curriculum, except when we get to doing our PhD theses, in which case suddenly we're exposed to having to do this with often very little training in how to do it.
I guess I'm curious about the connection between, so obviously in applied math, it's a separate department that's completely separate building from what we would call, say, pure math or math. And I'm curious what you see as do you see these fields getting farther and farther apart, or do you see, I'm in a department now where there's applied mathematicians and pure mathematicians, and sometimes I feel like I might as well be in a group with a department of philosophers. I'm just curious kind of what maybe you could speak maybe to what is going on here at the UW or more generally.
Yeah.
And maybe you fit into
I started
yeah.
out in the math department here, and I have to say I really enjoyed it because I learned a lot. I was teaching, classes in, say, analysis, and the students would say, well, how does this relate to what we were doing in topology? And I'm like, I don't know. So I moved to applied math just because, I feel more at home here. I go to the same meetings that applied mathematicians go to, not the ones that pure mathematicians go to. Even though my work is analysis of numerical methods, it's proving theorems. It's in a sense pure math. Are we moving farther apart? Well, that's a hard one. I certainly use tools from pure math in analyzing numerical methods. So in that sense, I still consult with people over there. I talk to people to find out some new theorem from complex analysis that I can apply to matrix theory.
I like what Eric said. We don't have prejudice. We see all these different tools, and if we know them already, we find that perfect tools for a problem. If we don't know them, we go and learn it, and we could take a sabbatical from what we were doing and learn a new field. So that's applied math. We don't have prejudice. And then also I like what Chris says, that in modeling, as Fred taught us in the modeling course that he pioneered, you set up a problem, but you don't specify a tool. You pick the appropriate tool to solve the problem. So as I am teaching the modeling course after Fred, I always tell my student, by hook or by crook, you solve it. But that's not the important part. The important part is the formulation of the problem, and then after you find a solution, what do you draw as conclusions from that solution, and how you improve the model. So we don't have prejudice. We just want to solve the problem by hook or by crook.
My question is sort of about what I interpret to be sort of a growing divide almost between academia and industry, especially as it relates to machine learning. So I'll give an example of what I mean. So I went to one talk a few months ago, and it was about an analysis of the algorithm used by Google for AlphaGo. For those of you who don't know what AlphaGo is, it's like a deep neural net, and it plays Go, which is, it's kind of a game of chess, basically, and it's like better than humans are at Go. And the whole point of the talk, basically, they go through some convergence results, and they show, like, in the original paper that Google published, they were using like an exponential function for some part of the algorithm, and they basically showed in their proof, like, well, it doesn't converge when you use the exponential function. You actually have to use like a square root instead for the convergence. But it turns out in Google's actual code, they were already using like the square root function in that place, even though in the paper, the proof they presented was using the exponential function. And the whole point of this is to say, like, from Google's perspective, you know, they're trying to prove, they know this algorithm works, and they were trying to prove that their proof had like some small problem with it. But when they were actually on the computer getting it to work, it was like, okay, well, let's try changing this line of the code, and okay, well, now it magically works. And I guess the question is like, you know, these people at Google, you know, they just changed some line, and it's like, okay, well, it works now. Whereas these other researchers spent like a really long time, like several months, trying to, you know, show why that should be the case. And obviously there's some value to that, but I guess my question is like, what is like the right problems to work on in academia? Like, I don't know. What are your thoughts? Does that make any sense?
So if I may say something. So from my perspective, I would say that the value in trying to understand why the square root works better than the exponential would be that once you understand that, maybe you can come up with something with that understanding that is even better. Right? And so sometimes maybe there's nothing better, but and that's valuable too, to know that. But in other cases, you will find something that is better.
I mean, this is the essence of academia. We're trying to figure things out. We don't have to make a profit. We don't have to beat the world champion of Go. So we can take the time to figure things out. And then, like Bernard said, once we get to the essence of it, with the theory, with all the machinery that was involved getting there, we have a possibility of you know, improving it. Or while we're analyzing it, actually discover something new and something better. So this is you know, we have that luxury here in academia to discover. After 10 years.
If I could just say something. I definitely agree with that, but I guess really what my question is are we in academia really asking the right questions? Like, are we trying to tackle the right problems? Like, it's not that, oh, these people like wasted their time. It's like, could their time have been better spent elsewhere? Maybe?
Well, I think anyone who does research, even in areas that are as eminently practical as atmospheric science, recognizes that 99% of research is probably, you know, getting at 1% of the impact, and that other 1% is going to be what's important. And the only problem is you don't know what that 1% is ahead of time. I mean, you guess. Of course, you work on things that you think are important, but and fun, hopefully at the same time. But I think again, just history tells us we can never know what's important. It's, you know, it's really interesting when explodes as being important that you had no clue was going to be important. And so, to me, as an academic researcher, you know, the great thing is you get to do things that are fun. You get to say they're important, but first and foremost, they're fun. So even if they turn out to be a bunch of bunk, at least they were fun while you did it.
Peter?
May I respond to that question a little bit with a counter question? I see working with students that if the answer is not a great success and you are basically nominated for Nobel Prize, it's not worth doing it, and it feels like time wasted. But I feel if a research result shows that a technique or an idea doesn't work and can clearly illustrate why it doesn't work, this is also very valuable knowledge that a company will never tell you that they actually went through that, and most students are afraid of telling their advisor that, and that is a mistake. I think it's a great discovery to know why something doesn't work, and that's another part where here in academia, that's what we should be doing. We should not just say, oh, this works and forget everything else, so everybody else has to do the same stupid mistake on their own. Let's all learn from our mistakes. That's part of why we are here, and help each other get better. And I know it may not be the right answer to your question, but that made me think very much in that direction. If your question is, are we doing the right thing? Are we asking the right question? Is this the same thing like saying, oh, I wasted so much time to prove that this didn't work? I think it's still valuable.
Is self-organization still a topic in the world?
We talk about it in clouds all the time. we see rain systems in the tropics organized on all kinds of different scales, and we ask why, and people have thought about that in terms of thermodynamics and critical points. They've thought about it in terms of hydrodynamic instability. They've thought about it in a lot of different ways. And so as long as you're looking at multi-scale systems, self-organization is a sort of a natural characteristic we look for in multi-scale systems. So I would say more than any time we're thinking about that.
Multi-scale.
Yeah.
So we are running out of time. Does anybody want to make any closing statements about anything they've heard? I mean, obviously, I think we've had a very good discussion. We could easily go on for another hour, but we don't have that other hour. I think one thing I've heard is that there's definitely a lot of stuff to do in the next 50 years. All right. I propose we thank all 6 panelists. And thank you for attending. And then if you go across the way to Meridian Hall, you'll